Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of graphing using calculus. You should have already watched my videos on the increasing-decreasing test and the first derivative test for graphing. And now we're going to start talking about second derivatives and concavity. And I'll start this with a definition and then we're going to visualize this definition. So concavity is a topic that may have come up in a previous course for you. Sometimes people don't talk about it until calculus, so that's perfectly fine. It's not necessary until now anyway. So if the graph of f, this is a true definition of concavity. So if you happen to know a definition of concavity that's different than this, it's because you have a good conceptual understanding of concavity, but it's not the true definition. The true definition of concavity: if a graph of f lies above its tangent lines on an interval I, then we say it is concave upward on I. If the graph of f lies below all of its tangent lines on I, it is called concave downward on I. Well, all right. I mean, I can give you a visual of that if you want. This curve right here is just a standard function, right? But let's start graphing out some tangent lines. And in fact, I'll actually just show tangent lines to this curve rather than graphing them out because it's a little bit easier for me to do it this way. So tangent line at this point, notice that, actually I will graph it. Notice the tangent line lies above the curve there, and I slightly missed the curve. Sorry about that. Notice the tangent line right here also lies above the curve. Notice the tangent line, let's say right here maybe, lies above the curve. The tangent line right here lies above the curve. So everywhere I'm doing this, the curve is considered to be concave down. Tangent line lies above the curve. Tangent line, let's do this, lies above the curve. So all these places you can see the tangent lines are above the curve. They're tangential to the curve. They touch the curve momentarily in that neighborhood. By the way, I should state that the tangent line, for example, this one right here, it does not always lie above the curve. It lies above the curve locally. And that's what we really mean by lying above the curve, is that locally, if I zoomed in, it's above the curve, right? But then there is a point where that kind of switches roles, and I'm going to use a different color for this. And that might happen, let's just say right about here. Let's just pretend I'm kind of graphing it roughly. And I should be using maybe a lighter ink as well, but for some reason I'm just not. But notice these tangent lines lie below the curve. So these tangent lines being below the curve means that the curve is concave up where we started graphing. So maybe right about, I'll say right about here, it switches to being concave up, and we use CU for that, as you probably guessed from me writing that. And prior to that, it was concave down, which we use CD for that. And a lot of students view this, and in fact I do as well, is if you have a curve that's cupped downward, it's concave down. If the curve cups upward, it's concave up. That's kind of how it is. If it's bending upwards, it's concave up. If it's bending downwards, it's concave down. So let's go ahead and use Desmos to visualize the concept of concavity. All right, so here we have our graph that I've been dealing with over this series of videos. I'm just going to drag this point. Actually, since I can do that, I'm just going to do it like this. So notice this is the tangent line and it lies above our curve. So this is considered to be concave down. And if I continue to drag that, you'll see there is a moment where it switches from being concave down to all of a sudden being concave up. And I wish I had it set to where it changed colors right there. It doesn't, but you get the point. Once it switches to concave up, it all of a sudden the tangent lines lie below the curve. In fact, I took a moment to do that. So now, hopefully, yes, there we go. All right, look at that. So here we go, where our tangent lines are above the curve, so it's concave down. And then at a moment here, it's going to switch to being concave up. Isn't that nice? And now watch what happens if I zoom out a little bit. Let me go ahead and we'll just go back to this one. I'm going to switch to concave up because the tangent lines are above the curve. Tangent lines are above the curve, and then suddenly they're below the curve. When it turns green, they're below the curve. And so it's all concave down on this interval right here, and then it switches to being concave up. It's all concave up on this interval. Switch to concave down, then concave up. So those points, by the way, where it's switching between concave up and concave down, those points are called inflection points. You may have heard the phrase inflection point, like our economy is reaching an inflection point, or the number of cases of COVID is reaching an inflection point, or something like that. That's when your rate of increase changes. So this rate of increase is growing and growing, and all of a sudden it changes, and it's still increasing, but it's slowing down. It's a slower rate of increase. So the slope of our tangent line gets lower and lower. And that brings us to the concavity test. The concavity test tells us that if the second derivative, and that kind of, by the way, relates to the language I just said out loud. I had said the rate of increase is slowing down, or the rate of increase is increasing. That is the derivative of the derivative that I was just talking about. So that would be the second derivative. And so concavity test tells us that if our second derivative is positive on an interval, then the graph will be concave upward on that interval. If the second derivative is negative, then the graph is concave downward on that interval, which is super nice because if you think about it, downward we often associate with negativity, upward we associate with positivity. So second derivative being positive implies f is concave upward. Now let's go ahead and prove this. Now this proof is going to be not terrible, but it's a little tougher to grasp, I think. So I'm going to go ahead and prove it just for A here. So proof of only A. That's all we're going to do here. And I'll graph off to the side here a little visual aid for us. So let me go ahead and pause and put in a visual aid. Now I hope you can agree that that curve looks to be concave up. And I'm just going to say that this interval, let's go ahead and just say from here to here, that interval we're going to call I. That's not that big of a deal. We know it looks to be concave up on that. We're going to go ahead and prove that if the second derivative is positive, then it is concave up. So this is how I'm going to start the proof. Now, mind you, I'm not really assuming my curve looks like that. I'm just stating like that's a curve and we have an interval. We're going to assume that the second derivative of that curve is positive, and we'll want to show that it must therefore be concave upward, or in other words, that it lies above its tangent lines. So let's write down the assumption. Suppose the second derivative is greater than 0 on our interval. Now we want to show that our function is concave upward, which means we want to show that our function lies above its tangent lines on that interval. So I'm going to create a tangent line to our function. And again, our function doesn't actually have to look like that, but I need this kind of visual for us. But we're going to create a tangent line at a point in the interval I. So we're going to assume that we have some point on the interval I, and that point is, doesn't really matter to me. Let's call it a comma f of a. So let a be an I so that a comma f of a lies on the graph of our function. So I'm just going to plot a point here. And again, this is not really the curve we're dealing with. This is the point a comma f of a. There we go, doing that. All right. And we want to find the equation of the tangent line at A. And we've done that enough in Calc 1 to be able to quickly write that out. So the tangent line looks like this. And of course, that just means that by the way, I put this in point slope form, right? It's y minus the y value of that point is equal to the slope of the tangent line times x minus the x value at that point. And now I'm just going to rewrite this in a different form that implies that y is equal to f of a plus f prime at a times x minus a. If your course or your instructor went through linear approximations, obviously this is what you used for linear approximations, the tangent line. So what we want to do is showcase that that tangent line always lies below this curve. Let me graph that tangent line in here, and I'll use red for that. There we go. We want to showcase it always lies below the curve. I'm not assuming it does here. I'm just showing you, again, this is a representative, maybe even not a representative example, but whatever. So I'm going to go ahead and do this. Now we're going to break this into two cases. We're going to look to the right side of A and showcase that our function has to be above our tangent line. And then we're going to look to the left side of A and show that our function has to be above the tangent line. Again, this is only going to be locally, so it's not going to be forever. It's just locally the curve should be above the tangent line is what we want to prove. So let's go ahead and do that. I'm going to zoom in here. So let's suppose that we have some x value that's greater than a, where the closed interval from a to x is a subset. That's what that means, subset of the interval I. So in other words, we're just saying that on this graph here, I'm grabbing an x value that's not at the edge of I. So it's a contained subset, okay? And that is important because we know the second derivative exists. That means the first derivative exists, which means the function must be continuous on the interior part of I, which will be very, very powerful for us. So let's go ahead and write that over here. So since f double prime is greater than 0, then f double prime exists. Therefore, f prime, whose derivative is s double prime, must be continuous on the interior of I. And since f prime is continuous, it exists, and therefore f must be continuous on the interior of I. And what does that mean? Well, that means, let's see, f is differentiable on the open interval from a to x, and continuous on the closed interval from a to x. So that's going to be very helpful because we can use, ta-da, the mean value theorem. So by the mean value theorem, there must exist some number in between a and x such that the slope of the tangent line at that number is equal to f of x minus f of a over x minus a. Writing that in the alternate form, which I always have to do, that implies that, let's see, f prime of c times x minus a must equal f of x minus f of a. Okay, not a big deal. Let's go ahead and just stick a pin in that. Pin, because we'll come back to that a little bit later. All right, so we have that equality set up. Now we're going to go ahead and step back into some theory that we have recently introduced. Since we are assuming that f double prime, where is that assumption? All the way at the top. Since we're assuming that f double prime is positive on our interval, then remember, by the increasing decreasing test, if f double prime is actually really the way the increasing decreasing test reads is if f prime is positive, that implies f is increasing, right? So if f double prime is positive, then f prime is increasing. Again, if you were to go ahead and just put an extra set of primes on here, you would see that's the same statement. So if f double prime is positive, then f prime is increasing. And that is by the increasing decreasing test. So I'll just write that by ID test. And that's going to be critical. So let's go ahead and use that piece of information. So note that C is in the interval from A to X. Well, that means that I'll even write that out. Since C is in the interval from A to X, C, well, it's greater than A, which will imply that f prime at C must be greater than f prime at A because the derivative is increasing. If you have a number greater than another number on the number line, because the derivative is increasing, the derivative at that greater number is greater than the derivative at that lesser number. I hope that makes sense. Just, as you read from left to right, the function's increasing. In fact, I think it might be easier to see it the other way around. So maybe we should write it the other way around. Just say this implies A is less than C, which will imply that f prime at A is less than f prime at C. Some people visualize it better that way. Now, another thing that I can say is since x is greater than A, we can multiply both sides of this inequality here by x minus A. This is going to seem really weird, but I get to do it anyway, just because I want to. So f prime of A times x minus A must still be less than f prime of C times x minus A. All I did was multiply both sides of this inequality by x minus A. The inequality didn't change because x is greater than A. So that's just a positive number I multiplied both sides of that inequality by. So that should not have thrown you off, or I hope it didn't. And then I'll do one more step here. I'm going to add to both sides of this inequality f of A. So I get f of A plus f prime at A times x minus A is less than f at A plus f prime at C times x minus A. Now I hope that you see something there that looks very familiar, specifically this piece right here. That is our tangent line. That's the equation of our tangent line. Oh, where the heck is that thing? It's way up here. Yeah, there's our equation of our tangent line right there. So I'll write it this way. This implies tangent line is less than that f of A plus f prime of C times x minus A. Well, that's pretty good, right? However, notice up where I said we're going to stick a pin in this for now. If you were to grab that equation right there that we stuck a pin in, and you were to solve that for f of x, you would get the following. F of x is equal to f of A plus f prime at C times x minus A. That's from where we stuck a pin in that up above. If you just add f of A to both sides, you get f of x is equal to f of A plus f prime at C times x minus A. And notice that picture right there is the same as this picture. And so we will have proven that the tangent line locally, tangent line, is less than f of x. It's below f of x. So with the only single assumption that our second derivative is positive, we've shown that to the right of A, our tangent line is below the curve, which is what we wanted to prove because that's what it says. Okay? Because being below the curve implies concave upward. Now, if you look to the left, instead of looking to the right, we would redo this. Well, you don't have to redo the entire proof. Maybe I'll write it down here. In the case where x is less than A, so now we're looking to the left-hand side of our graph, wherever that graph is, somewhere up there. Instead of looking to the right, we're looking to the left. In the case where x is less than A, then by the intermediate value theorem again, there exists some C in the interval x to A such that f prime at C is equal to f of x minus f of A over x minus A, yada, 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 right? We happen to know, again, it's still true that the function is still increasing. So f prime of C is now less than f prime at A. And if you multiply both sides by x minus A, in this case, prime at A times x minus A, the sign will switch because x is actually less than a. And so you get this going on. But otherwise, the proof is very similar. You just add f of a to all three sides. F prime at c, x minus a is less than f of a plus f prime at a times x minus a. The right-hand side of that inequality is the tangent line. And the left-hand side of this inequality is actually f of x still. So in both cases, the function lies above the tangent line, and so therefore we have proven, at least for part A, which is all we're going to do, we have proven that if our second derivative is positive, then our tangent lines lie below the curve. That is, by definition, the curve is concave upward. QED. So that is completely done. And as I mentioned earlier, a point on the curve is called an inflection point if, well, I didn't mention this part, but if f is continuous there, and the continuity is very important, so I'm going to highlight that. So if f is continuous there, that was supposed to be a different color highlighter, but my highlighter just likes to argue with me. So it's continuous there, and the concavity of the curve changes at p. So in other words, it changes from concave down to up, or concave upward to downward at that point. As long as your function's continuous, then you'll have an inflection point where concavity switches. I'm not going to bother going to Desmos for that one because I mentioned it when we looked at the application. So let's find the inflection points of the following function. And by the way, this is the function we've been dealing with this entire time. So all my previous work is on here. If you haven't watched the previous videos, rewind, go see those. But that's what all this ink is the previous work. Now to find the inflection points of this function. And the inflection points occur, remember, when the second derivative switches signs, or when it goes from concave up to concave down, it being your function. So that requires us to find the second derivative. So we'll write here f double prime, if I have an actual pen, f double prime of x. And I'll look at our first derivative, which was 8x minus 4x cubed. The derivative of that is going to be 8 minus 12x squared. And all we need to do here is find out where this is positive or where this is negative. And how I'm going to do that is by setting the second derivative equal to 0. Basically, I'm going to do what I did for the first derivative. Now, a little bit of a note here. I will often say, look for the critical numbers for f prime. The reason why I say that is because if you're working with a function, the critical numbers of a function f are where the derivative of that function is 0 or does not exist. Now we're not working with f, we're working with f prime. And the critical numbers of f prime occur when f double prime is 0 or f double prime does not exist. So they're the same definition. It's just now we're talking about what are the critical numbers of f prime, and that is just setting this equation f double prime equal to 0 or finding out when this second derivative doesn't exist. Well, it's a polynomial, it'll always exist. So we're going to solve, and let me make sure that I'm copying most of my language. Yeah, solve f double prime is equal to 0. Well, obviously, that's just going to get us 8/12, or what is that? Divide by 3 2/3 is equal to x squared. Let me just double check. 4, 12, yes. And take the square root. So you get plus or minus the square root of 2/3 is equal to x. So those are our critical numbers for f prime. That's where the second derivative turns into 0. That's kind of a weird way of saying it, but such is life. Now, notice that when we found the critical numbers for f, we set f prime to equal 0. We solved and we got these values here. And then we made a number line. Well, guess what we're going to do for the critical values of f prime? We're going to take its derivative, which we already did, f double prime. We set it equal to 0 and solved. And now we're going to create a number line. And I know there it is. So let's go ahead and create this number line, and this is going to be for f double prime. And in fact, I'll create it kind of high here. There we go. I'm going to try to match them up somewhat nicely. So remember, 0 was right about there. So I'm going to put a little teeny dot there so I know where 0 is. And negative root 2 was right there. So I'm going to put a little teeny dot where negative root 2 I plotted, and positive root 2 I plotted right there, which is not really symmetric, but whatever. All right. So now what I'm going to do, those little dots there, they really are not about f double prime. They're just my guidelines for placement. I'm going to plot the positive square root of 2/3 and the negative square root of 2/3, which will probably be right about here and here. So the positive square root of 2/3 and the negative square root of 2/3. Let me make that a better square root. All right. So we get to this point, and now we need to know what are the signs of the second derivative, because remember, we know now that our curve is concave up when the second derivative is positive and concave down when our second derivative is negative. So we have our second derivative staring at us right here. Pick wisely. For example, between negative root 2/3 and positive root 2/3, I'm going to test 0. And obviously that's 8, so that's positive. Notice I'm using the same conventions as I did with f prime, using the pluses above. And then pick any number below negative square root of 2/3, like a billion, negative billion, sorry. If you plug in a negative billion and square it, it becomes a positive billion, but times negative 12 is huge negative. So I know that it's negative over here. If you plugged in a positive billion, it'd be the same thing. Notice I didn't have to do math there. Now I'm going to write below those the ramifications. If the second derivative is negative, I know my curve is concave downward. And if my second derivative is positive, I know it's concave upward. Notice how I'm organizing my information. I align those two horizontal number lines to where they line up perfectly. In fact, normally I'd have them squeezed together a little bit better than this. And this will just help me in the long run for graphing. So I hope that makes sense. Now, to answer the question, find the inflection points of that function. Inflection points occur when the sign of the second derivative switches, or in other words, when you go from concave up to concave down, or concave down to concave up. Now, there is that little caveat with inflection points that f has to be continuous. Our function is continuous, so we're okay. So I'm going to make a little note here. This is an inflection point right here, and here's another inflection point. Now, it's not enough actually to just say the inflection points are plus or minus root 2/3. I think that you should really evaluate the function at those points, because that's what you're going to want to do in the long run. So the inflection points are going to be at f of plus or minus root 2/3, which is going to equal, what is my function? 3 plus 4 times that plus or minus. I'm writing it as a single plus or minus because they're being squared and then raised to the 4th power as well. So they'll be the same value. Plus or minus root 2/3 to the 4th. And this is going to be 3 plus 4 times 2/3 minus, let's see, 4/9. And let's go ahead and just go and compute that. In terms of ninths here, this will be, what is that, 27/9 plus 8 times 3, it's 24/9. And minus 4/9. That's 47/9. Okay. Does not reduce, but I don't need it to. But those would be the critical points. They're at positive root 2/3, 47/9, and a negative root 2/3, 47/9. Trust me, making a table of values like this is going to be very powerful in the long run. So back to our how-to. Given a function and asked to accurately graph, we're going to first find, well, not first, we're going to find the first derivative, determine the intervals of increase and decrease using that first derivative, and then use the first derivative test to indicate local extrema. If the derivative goes from, or the function goes from increasing to decreasing, you have a local max. If it goes from decreasing to increasing, you have a local min, as long as your function is continuous. Then you'll compute the second derivative, and you'll determine the intervals of concavity. It's concave up. If the second derivative is positive, it's concave down. If the second derivative is negative. You'll state the inflection points. That's where the signs of the second derivative swap, as long as the function is continuous. You'll organize your information and graph. And again, organizing is what I'm trying to do here as we move forward. But right now it looks like a mess because I'm sort of just doing this problem as we move. But the next time we touch this problem, I will have it a little cleaner. I'll start showcasing how you would organize this information. Before we get there, let's discuss the second derivative test. Yes, there is a second. There's not a third, so be happy about that, but there is a second derivative test. So it turns out that sometimes it's just easier to find a local max or a local min if you already know the second derivative. Now, to be honest with you, I don't often use the second derivative test. However, I remember when I was a student, I really liked it, but I just personally don't use it that much because I don't need to. Because it ends up not being super useful with the way that I do my graphing. So, but you'll still need it at times. So suppose that you have the second derivative and it's continuous. That's kind of the piece that's important. Your second derivative has to be continuous near to c. So if f prime of c is equal to 0, in other words, your function flatlines for a moment, and if the second derivative is positive, in other words, it's concave up, then, well, let's just visualize this. You flatline for a moment, and the second derivative is positive, so you're concave up. That should tell you have a local minimum. If your second derivative is negative, but you flatline for a moment, so flatline, but second derivative is negative, so you're concave down, you have a local maximum. Super nice. Pretty easy to understand. I don't really need to go to the Desmos app here either because I just drew it off to the side, so I'm not going to bother with that. All right, so let's go ahead and go back to our friendly example here and use a second derivative test to determine the local extrema of this function. We already know the local extrema, so I just want to state that. We already have computed the local extrema for this function, but let's just showcase how we would have done that had we used the second derivative test. Also note, before we begin, I've reorganized this page. Notice it's a little bit cleaner. Off to the left, I just have a couple notes here that normally I would not even bother writing if I was doing the, just graphing. I just wrote that for your information. And then I took the first derivative, set it equal to 0 or found the critical numbers. Took the second derivative, found the critical numbers. Made my plots, tested those, did the sign chart testing, labeled things like increasing intervals of increase, intervals of decrease, local max, local mins, intervals of concavity and inflection points. And then off to the left, I keep a table of values of all of these numbers. Notice, like, for example, I could have, I should actually, evaluate my function at 0. Well, 0 would be 3. So I have a local minimum at 0, 3. If you plug in a negative root 2, you'd get 7, and same thing with positive root 2. So I keep a table of values of all of the y values associated with all these critical numbers, because those will be the important points that I need to plot to help me really see what this function actually looks like. So everything is based upon critical numbers. Super nice. Now, the second derivative test tells us if our function is continuous. Our second derivative is continuous at or near c, then if f prime of c is equal to 0 and f double prime is positive, we have a local minimum, and so on and so forth. Well, if you look at our second derivative, it's continuous everywhere. I'll make that little note. It's continuous. I'll just make a little note here. It's continuous. So that means that I can use the second derivative test. I could totally use that if I wanted to. I don't have to, but I could totally do that. And the only usefulness of doing that is if you didn't already compute the local maxes or local mins. Notice that f prime of negative root 2 is 0, right? Because we have it plotted there. That just means that it's 0. Also, f prime at 0 is 0, and f prime at root 2 is 0. Again, that's from our sign chart for f prime. So that's where our derivative is 0. And now we're going to just look at the double derivative at those numbers. And I don't really need to compute it because I happen to know negative root 2 is right here. The double derivative is going to be negative. And the double derivative at 0, well, 0 is right here. The double derivative is positive. And again, f double prime of root 2, well, root 2 is right around here. The double derivative is negative. So this will tell me that, let's see, derivative is 0 at negative root 2, and the curve is concave down. Let me just showcase what that looks like. We flatline, but it's concave down, so we must have a local maximum at negative root 2. And if you look up above, we do have a local maximum at negative root 2. So this is just to showcase another way you could find local mins and local maxes. And there are some cases where this is more useful than using the first derivative test. F prime being 0 at 0 tells me we flatline at x equals 0, but it's concave upward, which means we have a local minimum. And again, that matches here. And finally, let me erase all this stuff. We have a flat line at f prime, or at square root of 2, and the double derivative is negative, meaning concave down. So therefore, we have a local max at root 2. You can see all that matches. So that's just to showcase another way to find a local min or a local max. Now, some people will ask, well, why would I choose one over the other? In fact, most students will ask that. When should I choose one over the other? You choose a second derivative test normally if you can't use the first derivative test. Or second derivative test is very powerful in theory problems where you're not being asked to graph, so you don't need to really find what f prime is and a sign chart for that, but instead you know stuff about the second derivative. Well, okay, then if I already know stuff about the second derivative and I maybe know that the first derivative is 0 at a point, then I don't really need to do the first derivative test. I can use the second derivative test. So it's a case-by-case basis, but you'll see I often use the first derivative test. So let's amend our list here. Given a function f, you're asked to accurately graph it. You'll compute the first derivative. You'll find the critical numbers and determine the intervals of increase and decrease, and then use the first derivative test to indicate local extrema if you can do that. The second derivative you'll compute. You'll find the critical numbers for that. Actually, technically, that would be called the critical numbers for the first derivative, but whatever. You determine the intervals of concavity. You state the points of inflection. And if you haven't found the local extrema, you could use the second derivative test to find the local extrema using that information. And then organize the information and graph. Now we're going to do a problem that I find to be kind of interesting, even though the text is all cut off. The following is a graph of f prime. That's critically important to note. So when you're handed graphs in calculus, you have to be very careful because the graphs that you're handed are not always the graph of a function. So in this case, there are graphs of functions, but they're not graphs of the base function. This is the graph of f prime. F itself is defined from -4 to 4, the closed interval. Now let's go through each of these step by step. State the interval or intervals where the function, not f prime, but where the original function, which we don't have, state the intervals where the original function is concave up. Well, I know to be concave up, the second derivative would have to be positive. The second derivative, though, is the derivative of the first derivative, isn't it? So if we're looking at the first derivative here, we're asking when is the second derivative, or the derivative of this function in blue, when is the derivative of this function in blue positive? Well, it's positive when it's increasing. So I know that, for example, over this part of the curve, the second derivative, which is a derivative of the first derivative that you're looking at, is positive. And by the way, it's negative when the first derivative is decreasing. So all this red area right there is, and it goes all the way down, by the way, is where the second derivative is negative. They're not asking for that, so I'm not going to bother with it, but that's true. And again, starting around here and climbing, as long as it's increasing, we know the second derivative will be positive. Looking over here, it looks to slightly increase, honestly, from here to here. So I'm just going to go ahead and say that the second derivative looks to be positive just in that little bit of a region. And then finally down here, from here to here, it looks like the second derivative is positive. Now I'm eyeballing this, so my numbers are not going to be exact. You just have to have some faith that you're not blind, basically. So let's go ahead. I'm going to use a ruler just to get a vertical view of this. I don't know where my, there it is, my degree sign. So let's see. I see that, try to get as accurate as possible. Yeah, probably up to maybe here and here. Okay. So the reason why I'm doing that is because we want intervals, x intervals, where our second derivative is positive. That is where our function, our original function, which we cannot see, is concave up. Well, that would be the interval from -4 to whatever this point is. And I'm going to say that point's roughly a -3.7. Let's just pretend. Okay. So from -4 to 3.7, it's going to be concave up. Now, just like intervals of increase and decrease, intervals of concavity will never include endpoints. So it is concave up, the function, when x is between -4 and roughly -3.7. And we're going to glue onto that interval the next time where our second derivative is positive, which occurs, I'm just going to erase this because I need that stuff later, which occurs from, it looks around -1.1 all the way up to, so our derivative is increasing, all the way up to, I'm going to stop at 1. There's a very specific reason. So from -1 to, or -1.1 to 1. Now you might be asking, wait, why did he stop at 1? Because it's increasing for a little bit up above as well. You're right, but our first derivative has a break, so our second derivative has a break. Our second derivative is not going to be continuous at 1. I'm assuming, by the way, that the x value for this jump discontinuity is x equals 1. So because our first derivative has a jump discontinuity at 1, our second derivative will be discontinuous at 1 as well. And because of that, I have to skip over the discontinuity and pick up on the other side of the discontinuity and keep going until about 1.1, to be honest with you. So I'm going to go ahead and say to 1.1. I'm eyeballing that. Let me go ahead and erase all that now. All right, and then the next time the second derivative is positive, it looks to be from around 3. I'll make it symmetric, 3.7 to 4. So union 3.7 all the way to 4, not including 4. Remember, it's always open intervals when you have intervals of concavity or increase or decrease. So that's how you would, given the derivative graph, state when the actual function is concave up or concave down. You look at the slopes of the derivative. Now here's the second question, right? State any values of the x values of the inflection points. Well, the inflection points occur when the second derivative changes sign. And the second derivative changes sign when the first derivative goes from increasing to decreasing, or from decreasing to increasing, right? So all of these values I'm circling, they have associated x values where our regular function has an inflection point. Again, we're looking at the graph of f prime, so the slopes of this graph are the second derivatives. And we want to know when the second derivatives switch signs. So the second derivative is positive here again. F double prime is positive, and F double prime is negative here. So I should put less than 0 and greater than 0. So it's the second derivative will switch signs at whatever this x value is. And I think we labeled that x value negative 3.7. So I'm going to say x equals negative 3.7. Technically, it's approximately equal to that. It also switches signs at this x value, which we said was negative 1.1. It also switches signs at this x value, which we said was positive 3.7. It does not switch signs at 1, but does a little bit later at 1.1. So I'm going to write that slightly out of order, but I'll put 1.1 right there. All right. So there we go. That's where our slopes change, or in other words, our second derivative changes signs. Where is f double prime undefined? Well, this is not a trick question, honestly. It's just, where does our first derivative not exist? And if our first derivative has a jagged edge, obviously derivatives don't exist at corners or cusps. So if our first derivative had a corner or cusp, then our second derivative would be undefined at that corner or cusp, but it doesn't have a corner or cusp, so we don't have to worry about that. But it definitely is not defined at a jump discontinuity. Derivatives do not exist at jumps. So the derivative of this function, which is a second derivative, doesn't exist at x equals 1. There we go. X equals 1. The next question is, when is the original function decreasing? Well, here is the slopes, f prime, of the original function. And as long as f prime is negative, we know our original function is decreasing. We need f prime to be negative. Well, let's look at where this graph is negative. It's negative all throughout here. It's below the x-axis, all through there and all through here. So though that's where our original function is decreasing. On the interval between negative 2 point something and point whatever, and again, 2 point something to 4. So let's go ahead and eyeball this. I would probably say that's a negative 2.3 maybe. So we'll go from a negative 2.3. And again, remember, intervals of decrease or increase do not include endpoints. So negative 2.3 all the way up to, let's see, when is this derivative still negative? That's almost like a 0.5, but not really, slightly above it. So I'll say a 0.6. A lot of eyeballing on this one. 0.6. And I'll glue to that the interval starting at 2.3 and going to 4. Going to 4. Union 2.3 to 4. That's supposed to not be a jagged edge there. All right, so not bad. And then the final question, not the final, the second to final, use the first derivative test to state any local extrema. Well, the first derivative test says that you have local extremes when the first derivative switches between negative and positive, or positive and negative. So when does our first derivative switch signs? Well, it switches signs right there, and right there. So we know that the first derivative went from positive to negative at negative x equals negative 2.3. So we have a local, let's see, it went from positive to negative. Okay, so we have a local max at negative 2.3. It's I should say at x equals negative 2.3. It also went from positive to negative at x equals positive 2.3. So put 2.3 there. And then we have a local min at x equals. Local minimums occur when your derivative goes from being positive or negative, to positive. that's when you have a local minimum. Double check that. If you have something that's decreasing and goes to increasing, definitely you have a local minimum. So you have a local minimum at that x value because the derivative went from negative to positive, or the curve went from decreasing to increasing. And we called that, what, 0.6, I think? Yeah. So local minimum at 0.6. All right. So that's using the first derivative test, or you could have used the second derivative test if you really wanted to. So use the second derivative test instead. And the second derivative test says, all I'm looking for is when my derivative is 0, which is right here, here, and here. And I want to look at the concavity at those points. So at x equals a negative 2.3, I think is what that was, are we concave up or concave down? Well, let's see. Negative 2.3 is not in that interval, so it must have been concave down. So concave down at x equals a negative 2.3 implies local max. All right, concave down, slope of 0. There you go. Next one. At x equals 0.6, our derivative is 0. Let's see. We said that the curve was concave up from negative 1.1 to 1. So we know that it's concave up at x equals 0.6. So concave up at x equals 0.6. So you've concave up, but it flattened for a moment at 0.6, means you have a local min. Now you can only do this if the second derivative is continuous, and it's not, but it's continuous near to 0.6, so we're okay. And finally, at 2.3. 2.3, our derivative is 0, but 2.3 is not where it's concave up, so it must be concave down at 2.3. So it's concave down at x equals positive 2.3, and it was flatlining at 2.3, so therefore it's a local max. A lot of stuff to kind of digest, right? This is a lot to put into your brain. I totally understand. However, it is critical that you get used to this. It is just one of those things that takes time to really do it. Now, we are going to stop this video. In the next video, we're actually going to use calculus to graph.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.